what are we made of? Ever since its beginning, humankind has tried to understand what the universe is made of. One of the very first people to dedicate itself to this study was Greek philosopher Democritus, who lived some 2500 years ago and put forth the idea that everything is made up of indivisible, indestructible blocks called atoms. Fast forward to a more recent time, we found atoms gone further inside them into atomic nuclei made of protons and neutrons, and even further in to their so far indivisible constituents, what we call quarks. Today, there is a whole branch of physics dedicated to studying the fundamental blocks of nature and their interactions with each other. We call it particle physics. The theory that reigns today was created in the 70s by a group of physicists and is called the Standard Model. Here, we identify three distinct groups: the fermions, divided in three generations and constitute all the visible matter in the universe; gauge bosons, which are the particles responsible for the interactions. We have first the photon, of the electromagnetic interaction. Second, we have the W and the Z bosons of the so-called weak interaction, which is responsible for phenomena such as radioactivity. And the gluon, of the strong interaction that holds atomic nuclei together like glue. Last but not least, we have the Higgs boson, which interacts with some of these particles, giving them mass. An interesting feature of this model is that it includes not only the particles shown here, but also its mirror versions with opposite properties, which we call antiparticles. These are connected by a transformation called CP transformation. If the physical laws are the same for particles and antiparticles, we say that the system has CP symmetry. When a particle and its antiparticle meet, they annihilate each other, releasing large amounts of energy in the form of radiation. A curious fact is that all theories of the creation and evolution of the universe agree that a short time after the Big Bang, equal amounts of particles and antiparticles existed. So, how do we exist? Because if particles and antiparticles annihilate each other and they existed in equal amounts, how did we end up in a universe made of matter? Somehow, the physical laws must have been just a tiny bit different for particles and antiparticles. If this happens, we say that there was CP violation. Now, this exists in the Standard Model, but it's nowhere nearly enough to account for the amount of normal matter that we see today. It then becomes very, very important to look for new ways to explain this discrepancy. This is done both theoretically, by extending existing theories or creating new ones, and experimentally, using very large and complex machines as very powerful microscopes. One of the flagship machines is the Large Hadron Collider, the LHC, located at CERN in Geneva. This is a 27-kilometer ring that accelerates and collides protons at extremely high energies, creating new particles via the famous Einstein relation E equals mc squared. At 4 collision points are very large detectors, working like big photographic machines to analyze the particles that result from these collisions. Now, even with the LHC, we still haven't found any significant deviation from the Standard Model, and we have simply been setting limits on different or new phenomena. This has led us to believe that if there are any discoverable deviations, they should be either out of reach of our current experiments or simply very, very small, and we have to keep improving our methods of looking at our results in order to be more sensitive to them. This is the main objective of my work. I will be looking at a very specific process with 1 Higgs boson and 2 W bosons, where so far no evidence of CP violation has been found. Focusing on the Atlas detector, one of the 4 detectors at the LHC, I will work to define a method to improve the current experimental sensitivity to these phenomena. I will start by performing simulations of real events with slightly different CP properties than the Standard Model, and I will later try to define the best way to analyze these events in order to maximize the possibility of either discovering or even measuring these different properties, if they happen to exist, or simply rule out their existence. Thank you.